A very good morning, good afternoon and good evening, my dear friends, students and participants for this course which is under NPTEL MOOC, the title of which is Application of Forecasting, Regression and Time Series Models. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, the three broad areas we have planned and we will cover in this course are forecasting, that is number 1, number 2 is regression and third part is time series. And we are in the second part which is regression models, and this is the 7th week which has just started, this is the 31st lecture. Now, what will be the coverage? Coverage is that if you remember we are discussing about multiple linear regression and we will continue discussing that, and we were discussing the implications in their more practical sense. So, what we mean by the expected value of the errors, we are discussing about the errors. So, if you remember the error has no dependence between them, and number 1 and number 2 expected value is 0, and number 3 is variance for all the errors is fixed and is given by either 1 or sigma square, and we also consider normality for the distribution of the errors. So, 0 conditional mean implies that the unconditional mean is also 0 in the sense that given x, we said that expected value of epsilon is 0. Now, it will be whatever the conditions if they are removed, still it will be 0. Also, this is important which we have mentioned, the covariance between the error and x is 0, that means there is no dependence between the error and x, each does not affect each other. So, that is also important, because that was one of the information we had given. That means, what are the information of x we are utilizing to predict. So, I keep using the word forecast, but technically forecast would be the forecasting concept, here it will be basically the prediction concept. So, whatever information is there in x would be utilized to predict y, and there would be white noise. So, white noise is not affecting the readings for x. Also, it would mean the expected value of x is equal to this one. So, if I write it in the concept of the beta means the values which I have for the regression coefficient. So, expected value of y, if you remember in the equation for the, I will derive it in the sense means go step by step. So, if I had the regression coefficient of one variable. So, obviously, I am not going to go into the details. Expected value of y, which is on the left hand side, would be expected value of beta naught, which is a constant, because for the population it will remain as it is, and it will be beta 1, which is also constant, into the expected value of x plus expected value of epsilon is 0. So, right hand side when you take the expected value, there are two terms. So, this is, when I use the green color to highlight this equation, is basically the multivariate form of the simple linear regression, in the sense that you are utilizing the multiple linear regression. We will come to that. Also, variance of epsilon given x is sigma square, which is homoscedastic. This is what I had mentioned, and I will come back with the diagram. In case it is not, it is heteroscedastic, which means the variance for epsilon 1, if it is time dependent, depending on the error, it is basically changing, and then it is basically heteroscedastic. Covariance of the error terms, if taken between them, is 0, then there is no autocorrelation or non-autocorrelation. In case if there is covariance between epsilon 1 and epsilon and 2, or epsilon I and epsilon j, whatever I and j is between 1 and n, if it is not 0, then there is correlation. So, again I mentioned the 4 points. One is concept of homoscedasticity, which means the variance of the errors dependent on x given x would basically be a constant term sigma square, and it is not dependent on time. And that means the error term of the past is not affecting the error of the future. But if it is affecting, then it is basically the concept of heteroscedasticity. That is the two important points. The other two important points is basically autocorrelation and non-autocorrelation or no autocorrelation. Autocorrelation means that the concept of epsilon I and epsilon j are dependent, and that is basically given the concept given by the idea of correlation, but that is autocorrelation means on itself. And no autocorrelation means that technically the correlation between epsilon I and epsilon j is 0. So, these four important concepts we will discuss. Now, definition diagram. A sequence of random variables is homoscedastic, homogeneity of variance, if all its random variables have the same finite variance sigma square, not dependent on time, which I mentioned in the last slide. A sequence of random variables is heteroscedastic, non-homogeneity of variance, homogeneity does not hold true if its random variables have different finite variance, that means it is increasing or decreasing. And here is the graph which I said when I was doing the last class, last to last class, because this concept of autocorrelation, no autocorrelation, homoscedasticity, heteroscedasticity are very important, mainly in time series and obviously in regression models. Now, you are considering homoscedasticity and heteroscedasticity, which is coming under assumption 4, all these assumptions. Now, along the x axis I have not marked is basically the reading number, and along the y axis we are taking the data as it is. So, if you see the red one, so they are superimposed over each other, the red and the blue. So, in order to give you a better understanding what does homoscedasticity and heteroscedasticity mean. If you check the red one, which is x2, that means there is variability. Yes, the mean value we are considering is 0, and the variability, if you keep finding it out any instant, like say for example, I find it at this instant or this instant, this is for the red one, not I am not coming to the blue one, at this instant or this instant, whatever instance I am finding out, the variability does not change, value is fixed. That is again I am mentioning is homoscedastic. But if I consider the plot of x1 which is shown in blue line, then if you check, I will use the dotted vertical one to signify to the information I am trying to glean or get from the red and the blue lines are at different points. So, if I consider this, let me use the color, so it will be easy. Let me use the green color rather than black. So, if I consider this or at this point, so if you see, and if it is normal distribution, by the way, for the blue one, the distribution is normal with a certain mean which is 0, and this is the variability. If I consider here, this mean value remains same, but the variability has expanded. If I consider the distribution here, the variability has much more expanded. But if I consider the red one, so mean value 0, variability is here, mean value 0, variability is also denoted, mean value there, variability denoted. That means the variability remains fixed, that means it is not expanding. Now, if I try to draw one graph, so with 4 different colors, and then come to that. So, I will erase this. So, this information of homoscedasticity and heteroscedasticity, I am sure I have been able to explain both in the qualitative sense as in the pictorial sense, as that things are clear. Now, if I am able to draw in this, so you have considered y axis, x axis. I will draw 4 diagrams. next to each other or one above left right, another two above below left right. Now, if the mean value is fixed, variability is fixed, the graph may look like this. I will use the mean value need not be at 0, but it is fixed. So, the mean value fixed and the variability fixed, the graph may look like this. Now, if the mean value is increasing not decreasing, increasing, but variability is fixed, the graph will look like this. If the mean value, so what is there in the x axis for all these 4 diagrams is time, and along the y axis we are plotting that values. Now, if the mean value is fixed and the variability is increasing, the graph would look like this. So, it is like, if I take it, it is like a cone, it is expanding. Here, if I take it, it is between a bandwidth, where the bandwidth is basically given to the variability, but this is the rate of increase is increasing. That is the trend which we have mentioned in forecasting. And if I take here again, between a band, mean value fixed. And if I consider both the mean value changing and the variability changing, let us use another color, violet. So, it means mean value is increasing and the variability also. So, amongst these 4, if I consider the one where variability increases is what has to be dealt more mathematically, and variability is not changing, that mean value is changing on fixed is easy to handle. Now, if you remember in forecasting, we did not mention anything about variability, all was about cyclicity, seasonality, trend, and regression models. I did mention about the variability, considering the concept of homoscedasticity, heteroscedasticity, the normality of the error terms with 0 mean, 1 variance or sigma square as variance. But in time series, we will actually deal with variability and specific for econometric and financial time series. So, all this discussion was going about for heteroscedasticity and homoscedasticity. Now, if I come to the concept of non-autocorrelation and autocorrelation, a sequence of discrete time series is autocorrelated if there is a correlation of a random variable with its past value. So, x t has some correlation with x t minus 1, or x t has some correlation with x t minus m. M means how many steps I am going backwards. A sequence of discrete time series is non-autocorrelated if there is no correlation of a random value with its past value. Now, if I plot them, and what I am going to plot is the same type of graph here, it will give that information about autocorrelation and correlation. By the way, these information or the graphs I am giving are based on simulated runs, but the idea is that they should give you the actual concept of homoscedasticity and heteroscedasticity, similarly for correlation and autocorrelation. Autocorrelation curves we have already done in forecasting. So, it should bring back some concept which you have picked up in regression. Now, if I plot a curve of autocorrelation function, this ACF is autocorrelation function, I am marking with the violet color, and if there is non-autocorrelation in general, the curve would look like this. In the sense, I will use the green one, which means it can be either positive or negative, because the autocorrelation values or correlation values is always between -1 and +1. So, if I plot it, you will find out the curve is just like this. General trend, which means there some part is increasing, decreasing. So, overall the correlation concept technically is not there much. So, these are basically dependent on lag. Lag means x t with x t minus 1, x t with x t minus 2, x t with x t minus 3. So, depending on the lag I am trying to find out. So, if I find out actually for the lag of 6 here, or if I consider say for example for 13, for 12, for 17. So, generally the autocorrelation functions are almost 0. So, technically if actually you have the autocorrelation function, the graph should have been like this. Again the sample autocorrelation, you have the lags, and if I plot it, the autocorrelation values would all be depending on the lags, would be all be on the x axis. Here there is some, but I wanted to point out that it is almost evened out. And these horizontal lines are the bounds, confidence bounds between which the autocorrelation values should be. But obviously, we know correlation has the values between -1 and +1. Now, if I go to this was for the non-autocorrelation, no such correlation exists between the random variable with respect to its past data as discussed in the previous slide. Now, if I come back to the concept of autocorrelation, you may think the graph looks same, but if you pay attention here, the concept of such type of symmetricity is not there. So, obviously, if you pick up any data in details, you will understand that, but in the same sense as in the last diagram, obviously, you may comment the 8th one autocorrelation is 0, similarly for the 18th one is 0, but in generally the dependence of positive negative as it was being evened out in non-autocorrelation is not happening in autocorrelation. So, autocorrelation means dependence on the past having an effect, correlation value being non-zero, and non-autocorrelation means obviously 0, and we have already considered the concept of heteroscedasticity and homoscedasticity in detail. So, this point is very important for time series, is important for forecasting, is obviously important for regression. So, I thought we have solved some problems, simple problems in autocorrelation. In forecasting, I thought I will discuss that with detailed diagram and definition time and again. We will revisit this when we do the problems. Now, coming back to the concept of the expected value of the error. So, if I consider the error, the matrix of the errors. So, why this matrix of the errors? Because when you are trying to find out the correlation, it is with itself and some past value, which is two random variables we are considering. So, obviously, for the covariance matrix, we would have the principal diagonal as the variance with it, which is basically the covariance of a random variable with itself, and the off the diagonal element would basically be the covariance of epsilon I with j, and it is symmetric because the covariance of epsilon I to j is equal to the covariance of epsilon j to epsilon I. So, if I consider this, the principal diagonal has the same variance because the concept of homoscedasticity holds. So, those values are fixed, it is sigma square, and the off the diagonal element, because we are considering the concept of non-autocorrelation, hence the off the diagonal element is 0. So, in this matrix at one go you are getting all the informations and the idea about homoscedasticity and non-autocorrelation. So, if I basically find out the expected value of epsilon square, which is basically variability variance. So, the variance comes out to be sigma square, and this capital I is the identity matrix, because why I am utilizing this symbol, because we are in the realm of multivariate statistics, which is basically multiple linear regression. So, variance of error is given by sigma square into I. Disturbance that meet the twin assumptions here I just mentioned. Homoscedasticity, because all the variance are sigma square. Non-autocorrelation, because of the diagonal elements are 0. If those two assumptions hold, then that property is important as known as spherical distribution. So, that means the errors would basically be on a type of spherical distribution, and this concept of normal distribution what we have stated would hold true, normal distribution for the errors. So, if you read the top part where the heading for each slide is there, I am going assumption by assumption. So, data on xi is random the same way as it is for yi's. So, xi means 1 to n, yi means 1 to n for the reading number. If xi is taken to be a random vector, then assumptions 1 through 4, which you have already done, becomes the statement about the joint distribution of x and y. Because reason being x, the errors is normal distributed, x's are all normally distributed, covariance structure between x's is such that they are uncorrelated, errors are uncorrelated with x's. So, once I try to find out the distribution of y, obviously it will be normal, that is point 1. Given these assumptions, I can find out the mean value of y given the mean value of x and error, that is point number 2. And point number 3 is that given the variability of x and the variability of epsilon, I can find out the variability of y, which means that for the simple linear regression, I will have the best fit line and the variability. Best fit line is basically the average value of y, and for the multivariate case, I will have the plane. The crucial assumption is assumption 3, the uncorrelatedness between x and y, because x does not affect epsilon, sorry, x and epsilon, x does not affect epsilon and epsilon does not affect x. We will assume that x can be a mixture of constants and random variables depending on how you take the reading, and the mean and the variance are both independent of all the elements of x's, in the sense that once you pick up any one x1, then it would not have an effect on x2 and vice versa. Disturbance are normally distributed, which I mentioned, with a mean value of 0 and variability of sigma square. This I means identity I am just mentioning because it is the multivariate case. A useful implication is the fact that observations on epsilon are statistically independent as well as uncorrelated. So, independent because if it is because you have a population from where you are basically picking up the errors, and the mean value of the errors you know is 0, variance is sigma square which is fixed, homoscedasticity rules, uncorrelated because there are so many number of readings in the infinite population that one does not affect the other, that means correlation is non-existent. Now, this graph is taken from econometric analysis by Green. We have done some analysis by drawing it on the go as we are discussing. So, along the x axis, I will use the black color, you have plotting x. Along the y axis, you are basically plotting y, but this bold slanted line is basically the mean value, which is alpha plus beta x. And if I find out the values, say for example, at any point of time and I take the horizontal line, this is the expected value of y given x is x naught. So, if I basically go vertically x naught, x1, x2, then based on the present value of x, here it is 2 dimensions, sorry, because there is only one x and one y. That is why the x can take values of x naught, x1, x2 till xn. Based on that, if I plot the expected value, that expected value is here for the case when x is x naught. The second expected value for y given x is equal to x1 is here. third value for expected value of y given x is x2 is here. Now, if you see all these normal distribution, normal why? Because the errors are normally distributed, the x distributions are normal, hence y would also a normal distribution. So, this is the distribution of y you have for each instant of x, and if you see the variability is fixed. And if you pay attention here, this is basically the distribution we are going to discuss more for the random variable y. One of the most useful models used is least square error concept, squared error loss concept. We want now, given this concept, we want to estimate beta naught to beta k, because that was the main task. In order to ensure that the errors of forecasting is minimized, and we have done that for the simple linear regression. So, our main task, minimize the error. Why? Find out beta naught to beta k. Find out is estimate beta naught hat to beta k hat. When I do that, I can find out these parameters and utilize them for the future calculation of y. Because say for example, the data set has 100 data points. So, consider I want to utilize those 100 data points to predict for the next time period 101. What? Predict what? Y values. So, utilizing those 100 values, I find out the beta hats, and then utilizing the beta hat values, and I use the 101 x value, and then multiply the beta hats with the 101 x value or the 101 x value, and utilize that to find out the 101 value of y. So, that is the predicted value of y. Then when I have 101 values of x and y, I utilize that to find out beta hat all values, and based on beta hat and 102 value of x, I basically try to find out the 102 value of y, and I proceed accordingly. So, which means, so here error of forecasting is minimized, which means we need to basically do the same concept as in the simple linear regression concept. So, here the diagram, again x along the x axis, y along the y axis, and if you have, say for example, the equation, actually the blue one which I am marking is the actual population, and when I estimate it, I have this. That means, I am trying to basically find out the estimate of alpha. Alpha is basically beta naught, alpha as A and beta as B. So, they are the counterpart of the sample, and when I basically plot it for any data, say for example, here which I am marking in black color, this is the epsilon from the central line, but when I basically put the best fit, this is basically E. So, counterpart of epsilon will be E, counterpart for beta here you see would be A. I will not go into too much confusion, but I am just saying what the diagram denotes. Counterpart for the betas will be given by B's. And if I plot the values, remember here, so this is basically the dotted one is the so called sample fit, and if I find out the corresponding values of y hat. So, y hat will be given by A plus Bx, because A is the estimate, B is the estimate, and obviously there is no error. And if I need to find out the overall difference from the actual value, so that would basically be given by, so this value is basically the actual x and y. And once I find out y hat, I find out the difference between y and y hat to find out the error. So, this diagram will be coming time and again, and if you remember in the Excel sheet, when we are solving the simple linear regression, I did discuss that. I will come back to that once more as we proceed. With this, I will end this 31st class, and thank you very much, and have a nice day.